Okay, so thank the organizers for inviting me here in this beautiful campus, and it's very nice to see how this place has come up. What I'll be talking today is essentially a reasonably old problem, and that's on the melting of vortex lattice in a type 2 superconductor. The only new thing here is that instead of doing standard bulk measurement, which is conventionally done, we will be looking at real space images of how these transformations happen. So these are the people who actually did the measurement. Somesh, Ganguly, and Indranil were primarily responsible for the real space images of the vortex lattice. Harkirat Singh did the complementary bulk measurements that we need to correlate. And the single crystals of niobium diselenide on which this work was carried out was synthesized by these people. That's a very central part of the work. Okay, so in nature, we are very familiar with periodic structures. The most common is a crystal. But in addition to that, there are also plenty of other periodic structures which are synthesized. For example, this is small glass beads in an aqueous solution. These are magnetic particles. And one common thing is that if you are at low enough temperature, most of these assembly of identical particles, they arrange themselves into an ordered fashion. There is no very fundamental theorem to prove that they will do, but we know in nature that normally they do. We also know, and actually these objects, the constituents, need not be physical particles. This, for example, is holes on an anodized alumina template. So in the process of anodization, the anodization doesn't happen uniformly over the aluminium. And you get this nice periodic hexagonal structure of holes in the alumina. Now, we also know that at high temperatures, typically solids melt, and they melt through a first order phase transition, and then they go into a liquid state. So let me define the problem that I will be primarily addressing. The problem is this, that if I had, let's say, a solid which is formed on a featureless substrate, there is no background potential. We know that normally this solid, like let's say a real solid, it melts through a first order phase transition. However, when we are talking of synthetic solids like these ones, which are these glass beads on a substrate in an aqueous solution, or these magnetic particles, there is almost always an underlying substrate which is not an ideal substrate. It's not completely flat and featureless like this, but it will have some unevenness. So that means this solid will also have a random pinning potential. There will be a random free energy landscape underlying. And what we will try to address is how the order-disorder transition gets affected when you have such a random pinning potential. All right, so our model system is the vortex lattice in a type 2 superconductor. I will not spend too much time on this. We know that there are this class of superconductors, which is all the compounds that we know, and niobium as an element, where you have a perfect diamagnetic state only at low field, and when you increase the field a little bit, you start having magnetic field that penetrates in the superconductor in the form of these flux tubes, each carrying one flux quantum. Now, if you look from the top, you will see that the structure is like this. You have this circulating current around the vortex, and the center of the vortex is a normal metal core. So these regions are superconducting, and wherever you have this magnetic flux going through, you have a normal metal core. These flux lines, they repel each other because they are like bar magnets which are the same polarity adjacent to each other. And the interaction between the vortices is given by this form, and don't bother about the specific form, but they arrange themselves through the interaction into an ordered lattice, and it's normally a hexagonal lattice which we call the vortex lattice. So we will use this vortex lattice as our sort of model solid over which we will study this order-disorder transition. Okay. Now, when you have, what is happening here? So, when you have a vortex lattice in a superconductor, then there is a very strange conundrum, because if you pass a current, there will be a Magnus force on the vortices, so the vortices will start moving in a direction perpendicular to the current. This will produce an electric field opposing the current, and therefore there will be power dissipation. So now you no longer have a zero resistance state, your superconducting state is destroyed. What saves us in practical systems is that every solid has some defects. These defects in terms of vacancy, substitution, impurities, and so on. Wherever you have a vacancy, wherever you have a defect, this defect works as a pinning well, as a potential well for the vortices. So the vortices will preferentially try to pass through a defect because that's where the condensation energy is lower. So these defects act as a potential minimum. Now if you have many such defects, you get a landscape like this, and this is what I called earlier the random pinning landscape. So now you will have the vortices which will preferentially sit at the minima, and you will have something which is like this. And if they are preferentially sitting at the minima, then when you pass a current, it has to overcome this potential well, and therefore you will have a finite critical current. Up to a certain current, the vortex lattice will not move, therefore you have a zero resistance, and then it will start moving. All right, so this has a problem. Is there any other of this? Okay, so now if you look at this cartoon, this is very similar to the cartoon that I showed before, with these balls sort of being replaced by these vortex lines, and therefore this is the model system that I am going to work with. Okay, so in specific, the system that we are studying is niobium diselenide, which is a layered superconductor of which we can make very high quality single crystals. And then to put these random defects and to have a control over the density of defects, we intercalate with cobalt, and these cobalts go in these interstitial sites between two layers. So they are sort of intercalated between the two selenium layers here. You can see these are three crystals. This is a pure niobium diselenide, some small amount of cobalt, a little more amount of cobalt. The Tc decreases a little bit. But in addition, what happens is that your pinning strength increases, this random pinning potential increases. This is the kind of crystal that we work with. Now, the crystal thickness that we are working with is between 60 to 100 nanometer. So one difference that we have here with the cartoon that I started with is that we have a three-dimensional vortex lattice, by which I mean that these vortex lines can bend significantly within the superconductor to accommodate these pinning sites, and therefore we don't have really a two-dimensional system. This is a three-dimensional system. So this is what we call a three-dimensional vortex lattice. Now, if you take such a system and if your pinning strength is not too strong, there is a very interesting phenomena that was realized quite early on. So you measure the critical current in the vortex state, and you see with increasing magnetic field or increasing temperature, the critical current decreases. But then suddenly it shows a very rapid increase, and then it reaches some value which is almost the same as the low field value, and then gradually comes down to zero at the upper critical field. This phenomena is called the peak effect, and let's see in a moment how this comes about. So if you had, let's say, if you had perfectly ordered vortex lattice, where your interaction, for example, is very strong, then this random pinning potential would do nothing to the vortex lattice because you will have equal number of vortices which are on the left side of the which is, for example, you will have equal number of vortices which are at the maxima of the pinning potential, at the minima, on the right side and left side. So there will be no force restoring the vortex lattice and your critical current would be 0. If you relax this order slightly, then each of these vortices will move a little bit and try to go to close to the minima, and therefore you will have a finite critical current. And if you have now a completely disordered state, then each vortex will go into the minima, and here you will have a very large critical current. Now, in the light of this, if you look back again at this, you can identify that this is happening because of the order-disorder transition of the vortex lattice. In other words, what we normally attribute as melting. And this peak effect phenomena is ubiquitous. It is not only in critical current, you can see it in susceptibility. Any property that of the superconductor that depends on the critical current, you can see in susceptibility there is a large increase suddenly in the diamagnetic response. In magnetization, you see the hysteresis closes, and then again close to Hc2, the hysteresis opens up like a bubble. This is again the phenomena of peak effect, which is manifesting in different forms. Yeah. So melting is actually used in a very loose way. It's not molten, it's an amorphous lattice. So it's also a glass. Yeah, that's correct. I think it should be glass here. I'll show you that later. So one can track, for example, this peak effect as a function of magnetic field and temperature and draw this kind of phase diagram where you have an ordered state here, now then you have a disordered state here, and then you reach the upper critical field. Now within this disordered state, whether there are additional line, whether there is a transition from a glass to a liquid and so on, these are outstanding questions. So to resolve some of these outstanding questions, what we decided to do is to look at the evolution of the vortex lattice in real space. So first let me show you how we do it. This is our toy that we are using, that we have been using. This is the TIFR milli-Kelvin STM that we are rather proud of. This is a home-built machine. It can go down to about 350 milli-K actually, and magnetic field we can apply up to 9 Tesla. It has a preparation chamber where we prepare the surface of the crystal, and then the crystal never is exposed to air. It directly goes inside the STM, and you do the measurement and you don't expose to air before all your measurements are over. If you want more details or if you want to build it in your lab, read this paper, all details are given here. All right, so the scanning tunneling microscope, I'll give you the basic principle. You have a surface here, a metallic surface, and you have a tip here, and it's separated by a very small distance, so you have a quantum mechanical tunneling current that can flow from this surface to the tip. Now if you move the tip, the tunneling current of course would vary because the surface is not smooth, and if you track the tunneling current, you will be able to get the topography of the surface. Now this is normally not what you do because this can crash your tip. Instead what you do is you try to maintain the current constant and you try to see how much you have to go up and go down. When you track that, then you get the topography of the surface, and you can do it with resolution which is atomic resolution. So this is an IBM diselenite crystal on which you can see individual selenium atoms, and you can also see the contrast coming from the 3×3 charge density wave reconstruction. All right, now how do we look at vortices? For vortices, what we do is that we have this superconductor here, we have this tip here, and what we measure, instead of the tunneling current, we measure dI/dV through a modulation technique. Now, if you measure at this point A, for example, you see that dI/dV looks like this. This is typical of what you get in a superconductor. You have the coherence peak, and here you have the suppression due to the gap. If you do at this point B, you see something similar, but when you have a vortex at point C, you see that it's completely flat because the vortex core is normal metal. So now what you do is that you stay at this voltage and you may keep on scanning your tip on the surface and you measure the tunneling conductance. So you will get a high tunneling conductance because of this coherence peak whenever you are away from the vortex core, and when you are in the vortex core, you will get a low tunneling conductance. So if you map this, you can get beautiful images like this. This is a high resolution images, this is a large area image. And you can see the Abrikosov lattice in a superconductor. All right. So now, before I show you the order-disorder transition, let me tell you there is a second effect of pinning other than giving you critical current, and that's the formation of metastable states. So let's say this is the kind of phase diagram that I have shown you before. And now I create the vortex lattice in two ways. First, I cool it in zero field and I apply 15 kilohertz here. I get a vortex lattice which is very well ordered like this. Instead, now I go to the same point, but I apply the field at high temperature and then I cool the sample. I get a vortex lattice like this, where all these red and white points are defects. Red is where I have a 5-fold coordination, white is where I have a 7-fold coordination. So you can see at the same HT point, I can have two different kind of states, and therefore I need to know which one is my equilibrium state. For that, I shake the vortex lattice by applying a magnetic field pulse. When I shake it here, nothing happens. When I shake it here, it transforms into something that is identical to this. So I know that this zero field cooled state, when I go like this, is the one that's the equilibrium state of the system. So this is important, and we will be using this scheme of pulsing in subsequent measurements. All right. So now let me come to the real data. This is the peak effect in our sample at 350 milli-K when we are ramping the magnetic field. So you have a peak effect which has an onset at 16 kilohertz state. It reaches, the peak of the peak effect is about 25 kilohertz state. So now I will show you how the vortex lattice evolves. So I start with 15 kilohertz state. I have a perfectly ordered vortex lattice, 6 Bragg spots from the Fourier transform as expected. I go to 20, so I have crossed this onset of this peak effect. I start getting these locations. These locations are adjacent points with 5-fold and 7-fold coordination. I go higher field, more dislocation. Here I have even more dislocation. But please note one thing, dislocation does not destroy my orientational order. So the Fourier transform, though the Fourier spots get broadened, they still retain the 6-fold orientation. So the 6-fold orientational symmetry is retained. Then I cross the peak of the peak effect here. And what I start seeing is these new kinds of defects which are isolated 5-fold and 7-fold coordination points. And so these are not pairs that are bound, they have sort of unbound. And now you see the Fourier transform is an isotropic circle. So I have destroyed my orientational order also. And then if I go further up, it gets further diffused, but both the orientational orders are lost. And it's only very close to HC2 that I see signatures of vortices moving, and that is why here you cannot identify individual vortices, but they become streaks because they are moving, and we are doing a measurement that's very slow. And this is possibly when close to the liquid state. All right, now let's sort of look at it a little more carefully. We have two kinds of defects that set in at different characteristic fields. One is dislocation, and the second is disclinations, which are these isolated 5-fold and 7-fold defect. And what I told you is that this one destroyed the long-range positional order but does not destroy the long-range orientational order. In this case, it destroys both. So one way to quantify this is to look at the positional and orientational correlation function, which is here you take the reciprocal lattice vector. For the positional order, you can quantify it through this quantity cos k dot r. If k is a reciprocal lattice vector, r is a lattice vector, then you know that this has to be 1 or a perfect lattice. If it is an imperfect lattice, it can be smaller than 1. So you do this average over all the possible r's that you have within your range. Similarly, to quantify the orientational order, you look at two bonds separated by a distance r, and if you have the angle between these two bonds as theta, for a hexagonal lattice cos 6 theta should be 1, and you do this average over all possible pair of bonds. Now, these two metric allow you to get perfect order when at large distances both these become 1. You can get long range order. So perfect order you would possibly get only at t equal to 0, but what you get is long range order where at large distances these go to asymptotic value, and you can get a disordered state where both these decay exponentially. But you can get also states that are in between, where one of these positional or orientational order can decay as a power law. So it will decay, but it has no characteristic length for the decay. So we try to see what they are for our system. And when we do that, what we see is at low field, this is a Bragg glass, and this is what is the hexatic state. Hexatic or nematic or twofold. Okay, so here at low field what we have is a ordered vortex lattice. We have a long range orientational order. The positional order seems to be slowly decaying. It could be a quasi long range positional order, but we cannot really find the functional form because here we don't have enough range. At low fields we have less number of vortices. At high field, which is above the peak of the peak effect, when we have disclination, we have a vortex glass, and here both positional orientational order decay exponentially. The interesting thing that we see, these two regimes are always, they were always speculated to exist, but what we see is something in between, where you have a very slow power law decay of orientational order, which means you have a quasi long range orientational order, but an exponential decay of positional order. So this is exactly what you expect in a hexatic state, and it's a state which is characterized by a long range orientational order, but no long range positional order. Now in 2D this is called a hexatic state. Since we are dealing with a 3D system, to contrast it, we call it a orientational glass. Now, before I go further into this orientational glass, let me just show you that we can also access all various metastable states. So you see, this was the curve that I was tracking before, but here you have another set of points. What are these points? These points are the field cool points. So these are individual points where you have applied the field at a high temperature, 7 Kelvin, and then cooled the sample to 350 milli-K at this field. So these data are not acquired as a sweep like this. They are individually acquired, and that is why you have the broken line connecting them. Now these are the field cool states, and in principle this is what I showed you for 15 kilohertz state before, that these have to be highly disordered metastable states. You can see from susceptibility that they are metastable states, because if you start from here and try to increase the field up or down, it doesn't follow this line, but it quickly goes and merges with the equilibrium line. Now these field cooled states, this image is here. Okay. So these field cooled states are defective states. And for example, 15 kilohertz state, which should have been a perfectly ordered state, here I see dislocations At 20 kilohertz state, where I should see only dislocations, I see disclinations. But recall that all these states, they can be just annealed by applying a magnetic field pulse. And if I apply a magnetic field pulse, they will go and join this state that I have shown you before. And yes, so that's the, I think that answers your thing. We have these glassy states everywhere. This is not a liquid in the conventional sense. Okay, now when does one see this kind of two-step transition or so two-step order disorder transition? The theory that exists is for the melting of a two-dimensional crystal, and this is a celebrated BKT HNY theory, which predicts that under certain condition a 2D hexagonal crystal can melt through two continuous phase transition. At the first transition, you have dislocations that proliferate, and at the second transition, this is wrong, you have disclinations. Oh, dislocations dissociate into isolated disclination, that it's correct, and you get an isotropic liquid. However, this is not really applicable in our system. It cannot be, first of all, because I have told you that this is a three-dimensional vortex lattice. Secondly, we have a random pinning potential, which is not what BKT considers. BKT considers a clean 2D system. And third important aspect, it is more technical, that here we don't have logarithmic interaction between vortices, at least at large distances. You have logarithmic interaction at very small distances. Now, to look for alternative, we can see that there are two routes to order disorder transition if we leave BKT aside. One is conventional melting, what we call as thermal melting. But the other, there could be another route which is a disorder-induced melting, but the melting is essentially, so when I am calling melting, it's a melting in a sort of loose sense, a ordered disorder transition which is driven by the increase in positional entropy due to random pinning. To see whether this, and this was proposed by Vinokur in this context, in a paper where he was mainly dealing with high TC materials. But to see whether this could be applicable here, we now measure various crystals which have different degree of pinning strength. So what we observe is this, that these are all done at 1.7 Kelvin. This is the crystal which is most disordered. This is where we start these dislocations coming in. This is where disclinations come in. And this red region is the hexatic state. Hexatic or the orientational glass. As we go to samples that are cleaner, then we see these two states, this state actually shrinks, these 2 points come closer to each other, and one would speculate that for a completely clean system, possibly there would be just one transition, one first order transition. You can also see the same thing in the phase diagram, where you see that this orientational glass, it shrinks as I go to cleaner crystals. So there is I think this gives us an indication that what we are seeing is essentially driven by the random pinning landscape. So now what we ask ourselves is, are these, if these are driven by pinning, are these at all phase transition? Now, of course, BKT predicts two continuous phase transition, but we know that this is not BKT. Regular melting is first order. So we ask ourselves whether these two could be two first order phase transition to start with. And one of the signatures of first order phase transition is across the phase transition you should have superheating and supercooling. Now there are other signatures like latent heat, which are considered to be confirmatory signature. They are much more difficult here because the background specific heat is extremely large. So measuring the latent heat over that is a very small change, and that might not be easily detected. So we tried to see if there is indeed hysteresis, if we can identify superheated and supercooled state across both these transitions. So for this, first we look at this lower transition, ordered state to orientational glass. So I prepared the state at point A here. it's a perfectly ordered state. Then I heat it to point B. So I have crossed this phase boundary. But still it is topologically ordered. I don't see defects coming in. However, this is a superheated state. And how do I know it's a superheated state? I apply a small magnetic field pulse, I shake it. As soon as I shake it, I see that I have dislocations that come in. Oh, sorry. Okay, I'll just finish it. So I have dislocations that come in, and I have gotten into the orientational glass state, which is the equilibrium state. Similarly, I can pull it back here, and what I see is when I pull it back, it should have been ordered, but it has dislocation. I apply pulse, and all those dislocations annihilate. I can do exactly the same experiment now with this phase boundary, and again I see effectively the same thing. Here I start already with dislocations at the lowest temperature, and then I heat it here. I have still dislocations, and my orientational order is not destroyed, though it should have been in the vortex glass because I have crossed this phase boundary. And indeed, if I shake it, I see that my Fourier transform has become completely isotropic. Similarly, I can pull it back, and I still see that it remains isotropic, but as soon as I shake it, it forms this six-fold orientational order. Now, okay, now there is a catch here because I am dealing with a glassy system, and I have hysteresis everywhere, so it becomes difficult to separate out hysteresis which is from the lack of glassy relaxation with the hysteresis from superheating and supercooling. So what I do to understand that is I prepare the vortex lattice here, and then I heat it without crossing any phase boundary. So here I am not crossing any phase boundary. I have some dislocations, and then if I apply a pulse here, I have more dislocation. But the important thing is that here the difference between this state and the pulse state is only numbers. I have not fundamentally altered the state. This was a long-range orientational ordered state. It remains a long-range orientational ordered state. On the other hand, in this case of superheating and supercooling, the symmetry has changed. One was long-range orientational ordered state, the other does not have long-range orientational order. All right, I think I will stop here. So this is my conclusion, and I will be taking questions.
Questions?
You measure the exponent as you approach the transition, and I guess that there's a universal value for that exponent for the orientational order. There's some universal value when you reach the hexatic transition.
You mean the exponent of the powered decay?
Yeah, exactly.
I see. Okay, I think we have not done that, so we need to look at that more carefully.
So the question is, so the picture that you show for this defects, etc., they are two-dimensional view, right?
They are two-dimensional view of actually a three-dimensional system.
Now, ideally, I would like to see that they talk about universal physics in every layer. So it's not very good idea that one layer says that it is orientational glass, the other tells it is.
Well, it's not here. The system is not very strongly 2D. So, structurally, though it has a layered structure, it's moderately 3D. So, you don't have, let's say, pancake vortices like you have in high TC. The point is our imaging technique cannot look at the entire vortex. It looks only at the vortex you see the endpoints of the vortices.
But how do I know? Because as you said that they can be very entangled in the three dimensions.
So a dislocation a dislocation, for example, there was some of these correspondence which were developed by Vinokur earlier. If you have two vortex that get entangled, then in a 2D plane, they manifest as a dislocation. The disclination is, I think, two vortex entangling and another vortex entangling this pair. If I am not mistaken, this I have to just check it again. But there is this, so these kind of defects, actually the defects are happening in 3D, but what I can see is only 2D, and that's the only technique that's available.
The thing is, you are talking about this proliferation of dislocation and disclination. So I thought the standard thing is binding and unbinding, and many things that we're calling dislocation having four dots, red, white, red, white. So which
okay, this is, yeah, so there are, could be, that's possible. And there are some of them which are dislocation pairs also.
And also for melting, I mean, first order melting, in terms of defects, there is this grain boundary, many things looks like a grain boundary lining up of.
Lining up, for example, you look at this. Here you don't see too many grain boundaries. In some of the images, for example, if you look at this image, I cannot really identify grain boundaries. So actually, we have discussed this before. We checked many of the data. I think one data looked more like, so here none of these, it is, so identifying individual defects is what we can do. If you have to now here identify a grain boundary, which one would you identify as a grain boundary?
How do I call? I can certainly identify red and white, we can distinguish. But beyond that, talking about
dislocation is not so difficult when you have adjacent red and a white. That is a dislocation. With, yeah, so now when you have four, that's the question which arises, what that four does. Yes, I don't know. I don't know. But there are so cases like, okay, I cannot find it here, but we can find it easily. So there are cases which possibly you are mentioning where you get things which are like a grain boundary, but they have been one-off. Yeah, but they have been one-off. So we don't find such grain boundaries when we look at many images which are, when we look at the statistics of images. Direction of the flux. So what we are measuring is not the flux. So we are not measuring the flux because what we are measuring is actually where there is a vortex core. So no, I cannot measure the direction of the flux. That is one of the major problems in this vortex lattice physics, that you have magnetic field probes, like for example scanning squid. But magnetic field probes don't have the spatial resolution at all close to this. Because here you have the magnetic field contrast is tiny. You have the penetration depth which is much larger than the coherence length. So the magnetic field variation can be of the order of a couple of %, which no probe can actually pick up at the moment. But what we are looking is the spectroscopy of the core. That is why we are able to see isolated vortices, because that's much more well resolved.
So, Pratap, is it true that there's no phase here where you see algebraic decay in both the positional and the orientational correlation functions?
Okay, that's a very interesting question. We, in some of the disordered samples, we had observed, so this is actually one such disordered sample. What we observed here, this is algebraic decay. And here there is an exponential decay, but if you believe this large distance decay, that becomes more algebraic.
I see. Okay.
So yes, it is not ruled out, but I cannot say with 100% confidence because this becomes close to the edge of the image, and the confidence level will.
not, let's thank Pratap.